I'm going to try to walk through the chalkboard problems from homework 13B as well as practice a review quiz with you. In this chalkboard problem, it's kind of one very large chalkboard problem. There is starting material, ethylbenzene, and we want to convert that into benzoic acid. And then we're going to attach a chlorine to the carboxylic acid to make an acyl chloride, and then we're going to do some other chemistry to produce a final product. The final product of this reaction, instead of telling you what it is, I gave you the spectroscopy that would show what that product is, and that might have made the whole problem kind of unapproachable for some of you, so we'll need to go to the spectroscopy when we get to that point. The first step is step A, trying to figure out what the chemical reagents are that you need in order to convert this ethyl group into a carboxylic acid. This is intentionally a review of a topic from Chemistry 351 in Chapter 12 of your textbook. So I've got here a figure from your textbook that shows the oxidation of benzylic carbons. This is on page 444 of your textbook, and what it shows are two different sets of reagents that will accomplish the oxidation at the benzylic position. Here is a benzene ring. It's got two benzylic carbons. One of them is a methyl group and one of them is an isopropyl group. In order for this oxidation to work, the carbon at the benzylic position, which is the position directly adjacent to the benzene ring, has to have at least one hydrogen. So if instead of an isopropyl group, this were a tert-butyl group with 3 additional methyl groups coming off and no benzylic hydrogen, then this reagent would only oxidize the methyl group over here. It just kind of cuts all of these other carbons off, turns the benzylic carbon into a carboxylic acid, and it's a pretty brutal chemical reaction. It kind of reminds me of a tree shredder, where you just strip everything down and turn it into a carboxylic acid. The two sets of reagents either involve sodium dichromate in the presence of hot sulfuric acid, or this is an acidic environment. Alternately, you can accomplish the same chemistry using potassium permanganate, aqueous, and this is generally a fairly basic reagent. And so instead of producing the carboxylic acid, the potassium permanganate will produce a carboxylate, meaning that the hydrogen isn't present. So that's why there is a second step when we add in hydrochloric acid, just to kind of cap off that oxygen with a hydrogen. So if you choose to use this set of reagents, then it's one pot and you're done. And on paper, that's quite a bit easier. If you choose to use this set of reagents, remember that in step 1, you have to use the potassium permanganate, and then in step 2, you have to treat it with an acid to put the hydrogen on the end. Either sets of reagents will accomplish the chemistry that we need to happen. So let's go back to the problem. We just need to take that carbon and turn it into a carboxylic acid. So for step A, it asks for missing reagents. You can either use the sodium dichromate in hot sulfuric acid or a 2-pot reaction where part 1 is to add the potassium permanganate and part 2 is to add H3O plus or HCl. Either one communicates that you're just putting a hydrogen gently on something that's mildly basic. All right, for step B now, we need to convert this carboxylic acid into an acyl chloride. And that was the lengthy mechanism that we looked at the end of yesterday's lecture, of lecture 13B. And that's using thionyl chloride and pyridine. So let's pull that lecture up. Okay, here's the thionyl chloride mechanism. Reagents, in terms of reagents, we can start off with any generic carboxylic acid, and by adding thionyl chloride in the presence of pyridine as both your solvent and a catalytic base, we convert the OH group into a Cl. So this is not a 2-pot reaction. There are 2 things that go into this in kind of a single reaction condition. So just SOCl2 in the presence of pyridine is sufficient to show the reagents. I think the question asked for the mechanism in step B. Yeah, we'll walk through that again in just a second. So at this point, you should know which reagents to add in step A and which reagents to add in step B. In order to know what reagents to add in step C, we have to figure out what the product is, and that involves some spectroscopic evaluation. So anytime you're given the standard 4 set of spectral data, so here's the infrared, the mass spec, the proton NMR, and the C13 NMR, and you don't have the molecular formula, the first thing you need to come up with is your molecular formula. The mass spec will give you some parameters to work under, primarily the molar mass of 182. That's a lot of molar mass to work with. And when you look at the mass spec data, this is 100 and let's see, 76, 7, 8, 9, 10. So that's 180 right there, 181. So this is my molecular ion peak right there at 182. And the reason that I always go to the molecular ion peak is I want to kind of figure out what's going on around it. So what you'll notice with the molecular ion peak are a couple of things. One, it's an even numbered value. So chemistry, organic chemistry is comprised primarily of hydrogen, oxygen, nitrogen, carbon, and halogens. Honk X. Those are the atoms of an organic chemist. If the molar mass is even, then it tends to not contain a nitrogen. Or said, I guess better, if it's an odd value, then we expect to have an odd number of nitrogens. Since it's an even value, I don't expect for nitrogens to be present. If there are halogens, they're either going to be chlorine or bromine. Those are the two primary halogens that we encounter. And both chlorine and bromine produce what are called M+2 peaks. The molecular ion peak is referred to as the M peak, and an M+2 peak would be a peak that shows up 2 units of mass greater than that. So here, there is no significant peak 2 units of mass larger than the molecular ion peak. The absence of M+2 peak eliminates, or not entirely, but strongly argues against the presence of either chlorine or bromine. These M+2 peaks occur because chlorine and bromine both have a standard isotope. For chlorine, it's chlorine-35 is the most common isotope, but there's also another isotope of chlorine, chlorine-37. Bromine has an isotope of 79, which is the more common isotope, and then the less common isotope is bromine-81. Notice how the molar mass of those isotopes differs by 2. 75% of all chlorine is chlorine-35, 25% of all chlorine is chlorine-37, and for bromine it's like 52 and 48%, roughly 50-50, 48. I don't know why I need to finish that. Okay, so what this means is that if you have a chlorine, you will see a molecular ion peak, and then at the M+2 position, there will be a peak that's approximately 1/3 as tall. So it would come up to about right there. If it's a bromine, then you see a peak at 182. You would then see the other peak approximately the same height, a little bit shorter, and be about the same height. So they're not there, so I don't think that I have a halogen, which matters because if you look at the reactant, there's a chlorine that's present, and then in the product, that chlorine is gone. And you're welcome to cheat and look at the title of the homework as Friedel-Crafts. So Friedel-Crafts acylation reactions typically involve attaching some aromatic ring system to an acyl chloride. So just based on the absence of the chlorine in my product and the title of today's homework, I'm guessing that I'm going to, in step C, I'm going to attach some type of aromatic ring system to this carbonyl group. That's what we typically do in Friedel-Crafts acylation. So if that's the case, well, what else can we know? In the in the mass spec, I have 182 units of mass. That is a lot of mass to deal with. One thing that you look for in mass spec is typically gaps. So to go from this 182, that means that the molecule is shattering and it's losing mass to produce a peak at 105. The difference in mass is a fragment that broke off. So remember, in mass spec, you ionize your molecule and then it shatters. The unshattered molecule is the molecular ion peak, and then these other peaks represent the fragmentation. In order to get from the molecular ion peak to 105, you had to lose 77 units of mass. And then the 105 shattered to produce something that weighed 77. That's where that peak's showing up. And this is 28 units of mass. Okay? In mass spec, whenever you see a substantial gap of 28, and what I mean by that is there's two fairly large peaks, and the difference numerically between them is 28, that often means that you had a carbonyl group, carbon-oxygen in your compound. Carbonyl groups often break, so if you have a carbonyl group somewhere in your compound, right there, and there's something on one side of the carbonyl group, we'll call that R1, and then there's something else on the other side of the carbonyl group called R2. In a mass spec, what tends to happen is one side breaks off, and then the carbonyl group breaks off, and you're left with R2. In this case, R1 is something that weighed 77 units of mass, and that broke off. And then the carbonyl group broke off, and it weighs 28 units of mass. And what you're left with is something that has 77 units of mass. Well, 77 is the mass of a benzene ring with 5 hydrogens. Can't draw a benzene ring. So a monosubstituted benzene ring with 5 hydrogens weighs 77 units of mass. So what this looks like to me is that my final product is just 2 benzene rings that are sandwiched around a carbonyl group. And I got all of that from the mass spec, but more importantly, from cheating. Knowing that this is going to be one of the fragments that goes into my product, which is a carbonyl group adjacent to an aromatic ring, and that the title of the homework is Friedel-Crafts acylation, which is a reaction where we plug aromatic rings into acyl chlorides, bumping the chlorine off and replacing it with an aromatic ring system. So just based on the name of the homework assignment, I kind of figured that I've got whatever this thing is without the chlorine plugged into some type of aromatic ring. Then I started looking at the possible fragmentations, and 77, 28, 77 as the major pieces that break out of that are common when you have carbonyl groups. I can look at the rest of the spectroscopy to confirm this, and more often with spectroscopy you have a proposed structure and you're just trying to show that you can't prove yourself wrong. In the proton NMR, I just have a flurry of peaks that show up between 6.5 and 8.5. That's standard for a benzene ring. So I just have a bunch of benzene hydrogens, which is nice. That means that whatever these units of mass are, there are no hydrogens that are not part of a benzene ring, which is absolutely consistent with my proposed compound. The C13 NMR makes me a little bit nervous. I should probably check the answer key before I start this, so I'm not nervous and I know what the answer is. But I'm pretty sure this is what I came up with as a question years ago, a younger brother sergeant. All right, so here we have our proposed compound. Okay, this carbon right here is a ketone, and ketones typically show up right around 200. Each of these benzene rings are chemically equivalent to each other. This is symmetrical. And in the benzene ring itself, this carbon is unique, this carbon and that carbon. I'm trying to put a number 2 there. These 2 carbons are the same. Those 2 carbons are going to be the same, and then that carbon is the same. So what I mean to show here is that I only have 4 types of carbons in my benzene ring. And since the benzene rings are equivalent, there's only 4 total types of benzene carbons. So this is probably the best evidence that this is my final structure. The infrared spectroscopy shows me a carbonyl peak at 1700, carbon-carbon double bonds at 1600, and nothing below 3000 here means that there's no sp3 hybridized carbons, but I knew that already, mostly because I didn't see any carbons that showed up in the typical sp3 region in my C13 NMR. Okay, so the product of this particular reaction is this, this has a name. I believe it's benzophenone. So it's a ketone with a benzene on one side and a benzene substituent on the other side, which we call a phenyl group. So that's where the term benzophenone comes from. All right, so what reagents would I need in order to turn this acyl chloride into benzophenone? Well, I need a benzene ring and I need a catalyst. So that's a benzene ring. If it doesn't look like one, you'll take my word for it. And then the catalyst for these reactions is AlCl3. Wow, typing is getting worse. Not typing, drawing letters. Okay, So I have now a complete list of reagents that are useful for getting from this ethylbenzene all the way to benzophenone. And these series of chemical reactions are not actually hard to do in the laboratory. I believe that I've coached students on most of the chemical reactions here. Pretty straightforward synthesis. I did ask you to show the mechanism for step B and the mechanism for step C. Step B is step C is the Friedel-Crafts acylation mechanism, and step B is the thionyl-chloride mechanism. So you can go to this slide. In the video is where I showed this. And all we're doing is we're taking let's double check in step B, we're adding thionyl chloride to carboxylic acid that's attached to a phenyl group. So you can copy this mechanism exactly as it is, and instead of R here, you can just put a capital P and a lowercase h. And that is an appropriate chemical abbreviation for a benzene ring. In the first step of the mechanism, remember that the oxygen associated with the carbonyl carbon pushes into the sulfur and breaks the weakest bond on the sulfur. That's the pi bond. We end up with this large complex. I have drawn this hydrogen here suggestively to show that in the next step, the pyridine base is going to come over here and rip that hydrogen off. The electrons kind of cascade down. It actually flips the carbonyl carbon to the other position. And this is a common feature of carboxylic acid chemistry. All we've really done here is just deprotonate our complex to prevent the reaction, the first blue reaction, from undoing itself. Red just locks the equilibrium and pushes the reaction forward. That's what a catalyst is designed to do. Now this negative formal charge on the oxygen, which is not pleased, highly concentrated negative charges on oxygen are usually a point of significant instability. So that's going to collapse back down again and bump off a chloride ion. And we end up with a slightly happier complex right here. Then that chloride ion or some other chloride ion in solution is going to attack the carbonyl carbon, replacing that unfavorably negatively charged oxygen, which then drives the final step of the reaction. A Diels-Alder-like reaction, kind of a cyclic rearrangement of bonds to produce our final product right here. The acyl chloride is our final product. The chloride ion that gets ejected here and the sulfur dioxide are both inorganic. You don't even have to show those in your mechanism. When you get to these three blue arrows, you can just jump right to this acyl chloride. I kind of left bond angles weird, hopefully so you could see what I was doing there with my mechanism, but then I just kind of redrew that in a less broken fashion in terms of bond angles. So that was the mechanism for step B. The mechanism for step C is a Friedel-Crafts acylation, which is also in the PowerPoint. So let's back up a bit and go to, here's our Friedel-Crafts acylation mechanism. So we're doing the same mechanism. Instead of this as our starting material, you can just think about that as being a chlorine. And this is AlCl3 in the mechanism on the chalkboard problem. And instead of a propyl group, that's a phenyl group. So in your own mind, just scratch that off and call it a capital P lowercase h, and the bromine for chlorine, and mechanistically now we're the exact same. So there's a preparation step where the chlorine of your acyl chloride pushes into an aluminum. Then this thing collapses to produce the acyl cation. These two preparation steps of the Friedel-Crafts acylation are required for you to show because you're trying to tell the story of the relevant carbons. In the other electrophilic aromatic substitution reactions, you don't have to show the preparation steps for the nitration, the sulfonation, or the halogenation unless I specifically ask you to. And I will never ask you to show the preparation steps for the nitration or the sulfonation. It's only the halogenation one because it looks very similar to this that sometimes I ask students to show that. Okay, once we get to the point where we've got the acyl cation, now instead of using a toluene in our chalkboard problem, we're just using a regular benzene. So just ignore that line. The pi bond pushes into the carbon. We break the aromaticity. And then in the last step, the catalyst, which in our case now contains a chlorine, is going to break that chlorine off to go pick up the hydrogen, and we get to our final product. So using the PowerPoint slides from the lecture that this homework corresponds to, you can find the mechanisms for step B and step C. Obviously, the hard part in this chemistry is figuring out what the product is, and so that's why this is a challenging problem. Okay, I wanted to go and look at one more question, so let's close some stuff down. We want this. No, we don't want this. We don't need this. We do want to look. Here's a review quiz. So since we're not meeting for class because of the Rona, then let's talk about the review quiz that we would have done as part of the class. And this review quiz fixes a mistake that I made in the video that hopefully none of you heard or have already forgotten. And you'll notice we start off here with an alkene, and we're conducting ozonolysis, and then we're going to do a Wolff-Kishner reduction right here. And the purpose of this review quiz question is to show you the context, to show you a reaction that can be done by Wolff-Kishner reduction that is not related to electrophilic aromatic substitution. We looked at Wolff-Kishner reduction as a way of interconverting between Friedel-Crafts acylation and Friedel-Crafts alkylation. So I will go back to 13b, and remember that this wheel of electrophilic aromatic substitution reactions, so this was the nitration reaction, this was the sulfonation reaction, the halogenation reaction, the Friedel-Crafts alkylation reaction, which sucks, and then the Friedel-Crafts acylation reaction. And so because the Friedel-Crafts alkylation produces low yield, we prefer to do a Friedel-Crafts acylation and then a reduction. There were two different types of reductions that we do, the Clemmensen reduction and the Wolff-Kishner reduction. The Clemmensen reduction mechanism is unknown, and the Wolff-Kishner reduction mechanism is not part of this course. Ever. I think I alluded to the fact that we might look at it, and I reviewed it, and I hate it, so we're not talking about this one. I don't hate it. Anyway, moving on. This is normally where I pause the video, gather myself, and move on, but doing one take. So Wolff-Kishner reduction takes that carbonyl group, and just gets rid of the oxygen and replaces it with two hydrogens. So how does that relate to today's review quiz? So in this ozonolysis reaction, what's going to happen? Ozonolysis clips the carbon-carbon double bond, and so we'll just think about scratching that out. And the combination of both of these reagents right here ultimately will take that carbon-carbon double bond and replace it with two separate carbon-oxygen double bonds, like this. And in the case of alkenes, it turns that into an aldehyde. So 1, 2, 3, 4, 5, 6. So this would be the product of that reaction after the first two steps. We have two hydrogens right here. Now, obviously, the bond angles would force this thing to kind of enter a zigzag arrangement. There wouldn't be two aldehydes sitting right next to each other. Start flopping around in solution. Now, the Wolff-Kishner reduction is going to take both of these carbonyl groups and get rid of the oxygen and just replace it with two hydrogens. And so this is a very long process for us to go from an alkene to an alkane. You might ask, well, why did we go to all this work to go from an alkene to an alkane when we could have just done catalytic hydrogenation? And I would say, you fool, you've missed the key point. And that's not only did we take the alkene and turn it into an alkane, we also cut the ring system open. Making and breaking carbon-carbon bonds is always a big deal. With Friedel-Crafts alkylation and acylation make carbon-carbon bonds. Ozonolysis breaks those carbon-carbon bonds. So the final product of this reaction would just be hexane. This cyclohexene definitely has more market value than hexane, but we did it. We made something less valuable through this series of reactions. That's not the point of the quiz. The point of the quiz is to show you that the Wolff-Kishner reduction actually has wider application than just turning Friedel-Crafts acylation into a Friedel-Crafts alkylation. It can get rid of ketones or aldehydes and turn them into CH2 groups, or in this case, a CH3 group. A couple of other questions students have asked. Some of you are deeply concerned about spectroscopy. We'll get there. There's a lot of details to be learned with spectroscopy, especially if you're not that familiar with spectroscopy or if you've forgotten a lot of the material, and we'll definitely review that. And I'll try to do more reviews like that in the Chalkboard problems and in these videos.